$2 billion is the estimated valuation of a market currently emerging from the accumulation of global plastic waste. In the industrial environment, these massive quantities of discarded materials are not merely refuse, but are recognized as dense sources of hydrocarbons, where energy remains locked within complex polymer structures. Why would humanity continue to drill deep into the crust of the Earth in search of finite crude oil reserves? Traditional extraction methods require immense geological exploration. Yet an artificial oil field has been established directly on the surface through decades of plastic accumulation. This transition from disposal to extraction represents a fundamental shift in resource management. The process is only gaining momentum. Technological advancements have altered the perception of material that was once destined for landfills, converting it into a primary resource for the global energy industry. It is visible how chemical bonds are targeted to release the stored energy within the synthetic chains. One can notice the transition of solid bulk into liquid and gaseous states as the equipment gradually breaks down the molecular integrity of the polymers. At first glance, this material appears to be nothing more than environmental debris, but in reality, it serves as a high-potential feedstock for the production of synthetic fuels. The journey from waste to refined energy begins with the systematic collection and sorting of various plastic grades. It does not end at this stage, as the raw material must undergo rigorous preparation to ensure the purity of the final hydrocarbon output. Modern energy technology operates with calculated precision to reshape discarded trash into a stabilized and valuable energy resource. Transition to the next level. One can notice how automated systems categorize the intake, preparing the artificial ore for the thermal reactors, where the true transformation occurs. The transformation of these polymers into a viable fuel source continues as the industry expands its technical capabilities. Three main types of plastic dominate the potential for fuel conversion: polyethylene, polypropylene, and polystyrene. These specific polymers constitute the vast majority of consumer waste, including plastic bags, thin packaging films, rigid food containers, bottle caps, and various household products. Why are these specific materials chosen for such a complex chemical transformation? The answer lies in their molecular architecture, as they are composed almost entirely of carbon and hydrogen atoms. Their chemical structure remains strikingly similar to that of crude oil, which allows for a more efficient transition back to a liquid state. One can notice how the polymer chains in these materials react under extreme heat. But this is just the beginning. When these selected plastics are fed into a pyrolysis reactor, the thermal energy begins to work on a microscopic level. It is visible how the long, complex polymer chains are systematically broken down into simpler molecules of oil and gas. The process is only gaining momentum as the heat-resistant chambers facilitate this molecular dismantling without oxygen. At first glance, this technology appears to be a definitive answer to environmental challenges, but in reality, plastic waste remains a critical and growing global crisis. This specialized equipment can only process a very small fraction of the massive volume of plastic discarded every single year. Not every type of synthetic material is suitable for the reactor, and the initial investment required to construct a functional plant remains exceptionally high. Furthermore, the sheer speed at which global waste is generated continues to outpace the rate at which any current facility can treat it. Everything only gets more complicated when considering the economics of the operation. Automated systems monitor the intake to ensure no incompatible materials enter the thermal cycle. One can notice the steady movement of conveyors transporting sorted fragments toward the reactor core. However, this mechanical intervention addresses only the visible symptoms of the problem. The root cause remains firmly embedded in the enormous scale of contemporary single-use plastic production and global consumption habits. This leads to a fundamental technical and social dilemma. Should the conversion of plastic into fuel be categorized as a temporary energy solution or as an essential permanent component of global waste management infrastructure? The technology provides a functional pathway for material recovery, yet it operates within a system of increasing demand. Thus, the process concludes this phase of the discussion, as the material transition from waste to energy remains a subject of ongoing industrial evaluation. 75% of all plastic waste eventually reaches a destination where its energy can be recovered, marking the true beginning of its transformation into oil. Why is it necessary to include nearly every variety of polymer, rather than just the common bottles found in traditional recycling. The process gains momentum because this specific system does not discriminate between materials, allowing for a far more comprehensive recovery of resources than standard mechanical methods. Every supermarket shopping bag, thin food wrapping film, and discarded container serves as the primary feedstock for this chemical evolution. Municipal collection routes and neighborhood sorting bins serve as the initial arteries for this massive flow of material. Markets, shopping centers, and public collection points aggregate these fragments into significant volumes. But this is just the beginning. Alongside the domestic stream, industrial waste flows from packaging factories, molding facilities, and massive logistics warehouses. These centers generate enormous quantities of polyethylene films, polypropylene bags, and production scraps that are often defective or surplus. Because these industrial streams are highly uniform and consistent, they are usually collected under direct contracts, providing an ideal, high-density raw material for large-scale processing lines. Specialized trucks equipped with integrated hydraulic compacting systems arrive to transport the waste. One can notice how the compression mechanism activates, slowly crushing the loose plastic to maximize the load capacity of every single trip. This mechanical force allows a single vehicle to carry tens of tons of material, effectively turning thousands of individual bags and fragments into a dense mobile block of industrial feedstock. It seems simple to move waste across the road, but in reality, optimizing these logistics is what makes the entire energy recovery chain economically viable. The trucks arrive at the transfer station and begin unloading one by one within the designated receiving area. Tipping mechanisms tilt the massive trailers, while conveyor belts and heavy forklifts maneuver the discharged material into organized piles across the yard. The equipment gradually builds these mountains of raw material, which are now ready to be refined. Everything only gets more complicated as the transition to the next level begins. From these sprawling piles, the mixed stream is fed onto a primary conveyor belt to undergo the critical stage of automated sorting. Preliminary cleaning systems represent the first line of defense against contamination. Industrial magnets are positioned above the belt, pulling away steel wires, metal caps, and stray mechanical fragments that could damage the reactors. Next, powerful air streams blow across the moving layer, stripping away paper, dust, and cardboard fragments. This leaves only the pure plastic behind, which then enters a sophisticated polymer identification unit. It is visible how infrared sensors scan every individual piece in a fraction of a second to analyze its molecular signature. How does the system know the difference between a milk jug and a water bottle? Each polymer reflects infrared light in a unique pattern. The sensors detect the specific wavelengths for polyethylene, polypropylene, polystyrene, and polyvinyl chloride with extreme speed. Immediately after this identification, high-speed compressed air nozzles fire with millisecond precision, blowing each piece into its designated sorting channel. The process is only gaining momentum as the plastic is simultaneously separated by shape, dividing flexible films from rigid containers and trays. Tight control over the material shape is mandatory to ensure the stability of the chemical reaction in the later stages. Once the streams are separated by chemistry and form, they move to the baling stage rather than being fed directly into the heat. At first glance, the plastic appears ready for the furnace, but in reality, its loose and bulky state makes it impossible to manage during the feeding process. The hydraulic press chamber resolves this by using steel pistons to generate thousands of pounds of pressure against the material. No heat is applied during this compression, yet the volume of the plastic is reduced to a small fraction of its original size. After several tens of seconds of intense mechanical force, a solid plastic bale is ejected from the machine. These blocks can weigh from several hundred pounds to more than 1 short ton, depending on the specific industrial plant design. Saw films and rigid plastics are now locked into a single standardized unit. This makes handling by forklifts significantly faster and safer, ensuring the facility operates with maximum efficiency. These dense bales serve as the standardized units of fuel for the entire pyrolysis system. Instead of managing thousands of chaotic fragments, the plant operators now work with uniform blocks whose mass and composition are precisely documented. The camera glides along the rows of these finished bales, each one representing a concentrated source of future energy. This phase concludes the preparation, opening the road for the final chemical transformation into liquid oil. 880 to 990 pounds of liquid fuel oil are extracted from every 2,200 pounds of dry plastic feedstock. From the baling area, the compressed plastic blocks are transported by heavy-duty forklifts directly toward the feeding port of the pyrolysis reactor. Why is this specific chamber constructed as a thick-walled steel cylindrical tube? It would seem a standard furnace could perform the task. But this specialized vessel is fully sealed and wrapped in multiple layers of thermal insulation to maintain a stable internal environment. The entire system is engineered to create a strictly oxygen-free atmosphere where the material is not burned, but rather broken down purely by the application of intense heat. One can notice how the reactor door is equipped with high-temperature gaskets and a reinforced safety locking mechanism. But this is just the beginning. The feeding door opens for only a very short duration when a plastic bale is positioned correctly. The forklift pushes the massive block into the chamber, and the heavy door immediately seals shut to restore the vacuum. This operation is tightly controlled to prevent any atmospheric air from entering the system, because even a small amount of oxygen could cause immediate combustion instead of the intended pyrolysis. Inside the sealed reactor, the temperature gradually rises to a range of 800 to 1,000 degrees Fahrenheit. At this specific thermal level, the long polymer chains that form the physical structure of plastic can no longer remain intact. They begin to break apart into much smaller hydrocarbon molecules, which escape the mass as dense, hot vapor. The process is only gaining momentum. It seems simple to describe this as burning, but in reality, there are no flames and no ignition occurring inside the tube. Instead, the material undergoes a process of thermal decomposition, which functions similarly to distillation but occurs within a completely enclosed environment. The feeding rhythm of the plastic bales is calculated based on the specific capacity of the reactor, the internal volume of the chamber, and the desired conversion rate. Some industrial plants operate with a continuous feeding logic, inserting one bale every few minutes, while others run in large batch cycles. In all cases, the objective is to keep the process stable, controlled, and uniform. The hydrocarbon vapor generated inside the reactor is immediately extracted and sent into the cooling system. Heavier compounds condense first as the vapor moves through the pipes, changing from a gaseous state into a thick liquid and forming paraffin oil. This is the primary product and the most economically valuable output of the entire transformation. After the oil has been almost completely separated, the remaining lighter vapor continues deeper into the system and becomes pyrolysis gas. It does not end at this stage. Instead of being released or wasted, this gas is redirected back to fuel the reactor itself, helping maintain the necessary operating temperatures and significantly reducing the requirement for external energy sources. One can notice how the solid material left inside the reactor is simultaneously transformed into carbon black. This carbon-rich solid can be utilized either as a solid fuel or as an industrial raw material for various manufacturing applications. On average, the process yields about 175 to 265 pounds of combustible gas and a remaining portion of solid carbon-rich residue for every 2,200 pounds of input. Most of the energy originally stored inside the plastic is preserved in the form of oil and gas instead of becoming an environmental burden. Transition to the next level. While waste plastic is transformed into oil to recover energy, that oil does not simply stop at being a fuel. It begins a second life as an industrial raw material capable of returning directly back into the infrastructure of modern cities. What once existed as discarded packaging, bags, and containers now becomes part of the physical foundation we move on every day. This is where plastic-to-oil recycling goes beyond simple waste management and enters the world of large-scale construction materials. After the plastic is converted inside the pyrolysis reactor, the vapor is condensed and separated into different technical fractions. The heavier fraction of this plastic-derived oil behaves very similarly to conventional petroleum bitumen. It can be refined and stabilized to become a binder suitable for high-grade asphalt production. Rock is simultaneously crushed, screened, and sorted into precise size ranges at the asphalt plant. These two streams, the recycled plastic oil and the mineral aggregate, are about to converge at the mixing station. From the storage bins, the aggregate is released onto steel conveyors and carried into a massive rotary dryer. Inside this rotating drum, direct flames heat the stones to over 300 degrees Fahrenheit. It is visible how the aggregate tumbles continuously while high-powered fans extract every trace of moisture. Dryness is critical because even a small amount of water would prevent the plastic-derived binder from bonding properly to the surface of the stones. Once the aggregate exits the dryer, it is lifted into a multi-deck vibrating screen tower. Strong vibrations separate the stones by size with mechanical precision. Large pieces create the structural skeleton of the asphalt, while medium particles fill the internal gaps and fine material locks everything together. Electronic weighing systems measure each fraction in real time, combining them according to a precisely programmed formula. At the same moment, the heavy fraction of plastic-derived oil is being preheated to around 300 to 320 degrees Fahrenheit. This ensures it remains fully fluid as it flows through insulated pipelines toward the mixer. Everything only gets more complicated. This is the exact point where waste plastic becomes a functional part of road construction. Both material streams enter the forced mixer, which is a sealed steel chamber equipped with two massive counter-rotating shafts. In a mixing cycle lasting 30 to 45 seconds, the hot plastic binder coats every single grain of aggregate. The liquid fills microscopic gaps and forms a uniform asphalt blend. One can notice how the viscosity is carefully controlled, so the mixture is neither too stiff nor too fluid. A central computer system continuously monitors material ratios, temperatures, and mixing time to ensure consistency. When the mixing is complete, the hot asphalt is discharged into a heated surge hopper, maintained at about 275 to 300 degrees Fahrenheit. This stabilizes the mixture before it moves into hot storage bins, where mechanical paddles rotate to prevent material segregation. From there, specialized dump trucks receive the material, featuring fully insulated beds to retain the critical heat. At the construction site, the recycled plastic asphalt is laid by pavers, shaped by screeds, and compacted by heavy rollers. The difference is invisible, but fundamental. Beneath the surface lies energy recovered from waste plastic, now locked into the roads that carry millions of vehicles every day. This is the final transformation where plastic becomes part of permanent infrastructure. The material is ready to move to the next processing phase without haste. 100% efficiency is an impossible metric for any industrial chemical transformation, and plastic-to-fuel recycling is no exception to this physical law. Why must this technology be viewed with technical skepticism rather than as a universal solution? It only looks obvious that turning waste into energy is a net positive, but in reality, this process cannot be treated as a free pass to sustain unlimited plastic production cycles. At first glance, the system seems like a closed loop, but any deviation from strict operational standards during pyrolysis can lead to the release of toxic gases and volatile organic compounds into the atmosphere. The equipment gradually reaches temperatures where hazardous byproducts are formed, threatening both the local environment and human health if filtration systems are not perfectly maintained. But this is just the beginning. The oil derived from plastic through these thermochemical reactions requires extensive processing. One can notice how the liquid settles into various fractions. Yet if this synthetic crude is not properly refined and directed towards specific industrial purposes, it risks becoming a secondary source of pollution rather than a viable energy solution. The process is only gaining momentum globally, but it is not a moral shield capable of justifying the continued generation of waste. Used incorrectly, these advanced recycling facilities can unintentionally serve as a technical excuse to delay the fundamental changes required in how humanity manages plastic resources. Transition to the next level of understanding reveals that the depth of the problem exceeds the capabilities of a single technology. Therefore, the focus must remain on the precision of the chemical process and the rigorous standards of operation. Hazardous emissions and unfiltered residues are the physical consequences of a system designed without total containment. It is visible how the molten material reacts within the reactor chambers, requiring constant monitoring of pressure and temperature to prevent the escape of volatile substances. Everything only gets more complicated when the scale of production increases. The material is ready to move to the next processing phase without haste, provided the environmental safeguards remain the primary operational priority. 100% of the global plastic crisis cannot be solved by a single recycling technology, no matter how advanced the thermal transformation process appears. Why is it impossible to view this chemical conversion as a universal miracle for the planet? To the eye, the process of turning polymers back into liquid hydrocarbons looks like a total solution. But it cannot fully replace the extraction of crude oil from the earth, nor can it absorb the hundreds of millions of tons of synthetic waste discarded by humanity every 24 hours. This technology is not a total replacement for traditional fuel sources. Engineers understand that the current infrastructure operates on a scale that surpasses the capacity of existing pyrolysis plants. But in reality, the true significance of this industrial method lies in a fundamental physical fact that changes our understanding of materials. One can notice how discarded packaging and containers are no longer viewed as mere environmental liabilities during this transition. Inside every polyethylene bag and every single piece of rigid packaging, there remains a concentrated chemical bond containing real energy. The equipment gradually breaks these bonds down, proving that the material still holds power waiting to be unlocked. Everything only gets more complicated as the scale of production grows, but the core principle remains unshakable. Plastic is not merely waste, but a resource that has been temporarily diverted from its energy cycle. The process is only gaining momentum as more facilities begin to treat discarded containers as raw material for high-quality fuel. It is visible how the molten material transforms, leaving behind the era of simple disposal and moving toward a system where every discarded object is a potential source of power. Thus, the transformation of waste into a valuable resource concludes this phase of the industrial narrative.